Hi, and welcome to Econ 481. These videos were recorded while I taught the class over Zoom, but they were later edited so that the students' faces, their questions, and my answers to those questions do not appear. As a result, the videos are shorter than a normal lecture, and they may have unnatural transitions. But I hope you enjoy them anyway. Bye now. All right, well, then, I guess we are ready to start. Welcome to this third lecture on marginal treatment effects. And then mostly you are going to be based on these two papers that I'm showing here, in addition to Ed VYTLACIL's job market paper that I'm going to discuss as we move along. So let's recap a bit to see where we are and where we're going. So again, in this first part of the class, we're going to have 4 basic lectures. We added a 5th one that we're going to discuss later, but right now we are right here in the third one where we're going to talk about marginal treatment effects. And then once we understand what marginal treatment effects are, we are going to discuss the so-called parameters as functions of the marginal treatment effects and the so-called policy relevant treatment effects. All right, I said we're gonna once we know what the marginal treatment effects are, we're gonna see how we can use these marginal treatment effects to define parameters as functions of the so-called marginal treatment effects, and then we're going to introduce the concept of policy-relevant treatment effects. So the outline for today is going to be, first, we're going to talk about VYTLACIL's equivalence result. We're going to see why that's going to be important. That's going to give us, some framework to say why we could be interested in something like marginal treatment effects. And then we're going to go through the marginal treatment effects, the policy-relevant treatment effects, and an empirical application that is taken from this second paper. All right. We're gonna start with this paper that I mentioned towards the end of the previous discussion, which was Angris, Imbens, and Rubin, which they argue that the interpretation of the error terms, which are the U in the notation that we're using, is difficult to understand. So they make an um, explicit reference to latent variables. Okay, so when you just have models that model unobservables in sort of like an explicit way by adding this U and so on, whereas if you just go to the potential outcomes, the unobserved feature is just embedded in the potential outcomes, which are by nature unobserved, right? That paper, they argue that assumptions about latent variables are hard to interpret. Okay, and so what we're going to discuss today is that if you recall, when we talk about latent variables, we have this selection equation, right? That says that an individual will choose D if this heterogeneity and observed heterogeneity U does not exceed a threshold nu of C, where Z here is going to be our instrument. And then we said, well, we can define potential treatments here just by fixing a value of Z, and that will just give us this indicator that U is less than or equal than B at that particular value of C. So in a way, we're saying, look, if you have an index structure like this, then you can have the potential treatment notation in Imbens and Angris, and then it looks like you can go from one to the other one. But the other way is not so obvious, right? That you can just take the late framework and say that that belongs to a family of latent variable models. So this was the initial sort of discussion. So this paper by Angry Simmons and Rubin made the argument, page 450, that monotonicity has no explicit counterpart in the econometric formulation. By econometric formulation is this that is associated with the Roy model and a number of papers by Jim HECKMAN. This statement was shown to be wrong by Ed VYTLACIL's job market paper. Ed is a professor at Yale, and he was a student at Chicago, a student of Jim HECKMAN. So what Ed showed is that monotonicity is equivalent to a Roy model with a separable index. Okay, so if you just look at this model over here, you can imagine that more generally, you could have D could be the indicator that some function, let me just say G of U and C is less than or equal to, right? So you can think about a model more generally like this. Um, so what this paper shows is that if this function here is separable as like whatever g1 of u plus g2 of z, then this model over here and the late framework are 1-to-1. Okay, and so um, that's the main result. We're going to discuss that next. There are two models. I want to write them clearly so that you know what I'm talking about. First one is a model that I wrote here, IA or Imbens and Angrist, which has essentially four conditions, right? The first one is you have the potential outcomes that is called non-interference or whatever. Like, you know, you just get a treatment. You don't care what if other people are getting treated or not. Just each individual receives a treatment, and that determines what the observed outcome is. The usual equation that we write for potential outcomes. Second one says that there are potential treatments as well, and that the observed D is just, you know, the value of your potential treatment given the value that you got for your instrument, here Z. The third condition is a so-called monotonicity condition, and I will say for any two values Z and Z prime, DZ is greater than or equal than DZ prime almost surely, or the other way around. And then the last one is that the instrument is independent of the potential outcomes and the potential treatments. That's exactly what we discussed last time. Summary. Now we have the Roy model. The Roy model has condition 1, which is exactly the same as the other one. And it has condition 2, there's a selection equation, okay? There's a latent variable u and an unknown function u of z, okay? But here, again, we are using the representation we were using before. And the assumption here of independence of the instrument is that the instrument is independent of the potential outcomes and the unobserved heterogeneity or this latent variable u. What Ed showed in his John Markey paper is that these two models are equivalent. That means model 2 implies model 1. Easy, we're going to do it in the next line. Then the tricky part is model 1 implies model 2, okay, which I'm not going to do here because it's going to take space. But the paper is easy to read if you're interested, and it's not long. It's actually a short paper. So this is what we're going to do. We're going to take this Roy model, which is essentially this equation and this, and we want to show that these three conditions over here hold, because the first one is the same for both, right? So what we need to do is prove these three conditions, okay, just using essentially these two. And as I said, this is straightforward. So the first one, we're going to do the following. First, I'm defining the little z as the indicator of u less than or equal than b little z. Okay. And then it follows immediately that the observed d, you can write it as the sum of z on the support of z, indicator that your instrument is equal to little z times dz. And this is condition 1, 2. Right? So it's straightforward, but in this latent model, you can define a new random variable dc where you just fix the value of c, obviously, and then you have that the observed one is just can be written like this. Then note, I want to write here for any dz prime, we have that b of z is greater than or equal than, or new, I'm going to call it b of z prime, or b of z is strictly less than b of z prime. So there's a function, right? So when you give me two values of z, either b of z is greater than b of z prime, or the other way around. Like one of those is true. And we're going to use that. And then say like, note, I already said note. Then we're going to say b of z is u less than or equal than b of z. Okay. is going to be less than or equal than the indicator of u d of prime. I'm just focusing now on this case. Okay, if it's not this case, you can do the other direction, of course. True. And this is d of c prime. Okay, so 1.3 volts. And then last one for 1.4, we have the following. Just take the collection of all these potential treatments, and this is the collection of all the indicators u less than or equal than b of little z. Oops. And this you can write as a function of u. The only random variable in that thing is u, because the c's are just fixed them. I just sorted the values. If it takes 5 values, I just put the first one, the second one, the third one, the fourth one, the fifth one, and then we have these 5 dz's, okay? And so now the only thing that is random is u. Then we have the assumption that says y0, y1, u is independent of z. So this implies that y0, y1 on a function of u is independent of z. And this implies that y0, y1 on all these potential treatments are independent of z. This is exactly 1.4. So as you can see, going in one direction is really straightforward, right? So you would imagine that a paper that had this impact, was published in Econometrics, contains more than this. But the other direction is a lot more subtle, and it requires careful arguments, okay? And the other direction is the one that shows that you need this separability to obtain monotonicity. Okay? Otherwise, you don't obtain. Here we're just using it. It's obvious, but if you don't have it, it's not obvious. But that's it. What matters, not so much the proof or, these subtle arguments. What matters is this, which is these two models are just notation, as we said at the beginning of the class. At that point, you had to sort of like believe me. Now you have a result. Questions about this? All right, so we're going to talk about marginal treatment effects. This comes from 2 papers by HECKMAN and VYTLACIL. Okay, motivation is the following. As I said, VYTLACIL's result, the one that we just described, shows that nothing is lost from the Roy model. Okay, so it means that the same type of assumptions are used if you just decide to model things using sort of like a Roy model with latent variables, or if you're just sort of like a late guy, like to use the late framework, potential outcomes, and not say how the decision is made. I wrote at some point, and this depends on the setting. It is not a statement that holds universally, but in certain settings, okay, the Roy model may actually be easier to interpret, because if you want to model behavior, the Roy model is telling us something about behavior. This hopefully will be clear when we get to lecture 5, and that's part of the reason why I decided to add that lecture to the class this year. And the reason is that then you can interpret this difference, as we said in the first class, as latent utility, okay? And so you represent the choice of D as a person just, in a way, maximizing the utility. There are only 2 choices. You choose the choice that gives you higher utility. And that is something that we do in a lot of other settings. In the context of firms, okay, this could be like profits. And then you say, well, the firm will decide to enter the market or not if it gets higher profits by entering the market and, not otherwise, and so on. So it just makes really simple to describe behavior, whereas in the other interpretation is implicit. But again, in some settings, you don't care about modeling that part of the behavior. So what we're going to do now to talk about this marginal treatment effects is we're going to use this non-parametric Roy model, just have the potential outcomes as always, and we're going to be using this latent variable equation. Okay, notice that d is u less than or equal to b of z, and then we're going to use this independence assumption as in the representation that we described before. U is continuously distributed, and it's going to be normalized to a uniform random variable on 0, 1. This normalization implies that this b here is just going to be the propensity score. And everything is going to be conditional on x. So we're not going to have any other x's. When we get to the application, we'll have no choice to bring back the x's, and we're going to describe what's going on with the x's at that point. But for now, let me just focus on this, and I want to make this point here, that you can always normalize this to uniform, and that a consequence of that is that this b is the propensity score. So let's do that. Suppose, let's say, let u tilde be a continuously distributed random variable with CDF f u tilde. Okay? And let me say let v tilde of z be a function of z. Finally, say let d be the indicator that u tilde is less than or equal than b tilde. So this is the setting. We have a continuously distributed unobserved heterogeneity. I'm calling here u tilde. There's some function of the instrument that I'm calling here b tilde. I didn't say that u is uniform. I didn't say that b tilde is the propensity score. What I did say in the previous slide is that assuming that is without loss of generality in this case. And to see that, well, you can see that this is the same as the indicator where we're going to apply what is called the probability integral transform. We're just going to apply the CDF of u tilde on both sides. And as you recall, when you have a continuously distributed random variable and you apply the CDF to that random variable, you get a new variable I'm going to call u that is uniformly distributed. Okay? So actually, just to be clear, let me just call this u, and let's call this b of z, right? So then I rewrite this model as this. And then u here is uniformly distributed. So now, notice that the propensity score is the probability that d equals 1 conditional on z equal to little z, or is equal to the probability that u is less than or equal than b c conditional on z equal little z. Then remember that z and u are independent and u is uniform. So this is b of z, which leads us to the result that the propensity score is equal to this function over here. So at the end of the day, the marginal treatment effect framework requires you that if you have a selection equation that looks more complicated than this one moving forward, say, we're going to see some examples in some other lectures, that you can write or rewrite that model as a uniformly distributed random variable less than or equal than the propensity score. Okay, and if you're in that framework, you can apply the marginal treatment effect framework that we are going to describe today. I'm going to still use this new here for now on, but you know that they're the same. Okay? Any question about this? Okay, HECKMAN and VYTLACIL define the marginal treatment effect as follows. Marginal treatment effect is the treatment effect, the average treatment effect for those individuals that have u equal to some number little u. You fix the unobserved heterogeneity. Suppose that you think about types. You have types of individuals, right? So you're going to fix the type. And then you're going to think about what's the average treatment effect for individuals of that type. Okay. I wrote here MTU is the average treatment effect for those agents with first stage unobservable u. Okay. Those with a small value of u, close to 0, are often choose D1. So the smaller the u given our selection equation, it's more likely that this is equal to 1. So there are people that tend to choose 1. People with large values of u are people that tend to choose 0. Okay. Of course, you can flip it around. If, like, once you put names to this, you say you capture something you care about, skills or whatever. Sometimes you will write them all as u greater than or equal than the threshold because it makes more sense. That's of course arbitrary. And so, um, notice that what we're saying here, based on everything that we discussed before, is like there's unobserved treatment heterogeneity if and only if there's a non-constant marginal treatment effect. Suppose that this marginal treatment effect, which is a function of u, and you would be able to say to plot it as a function of u, and suppose it is flat. Well, if it is flat, it means that there's no unobserved heterogeneity. People of all different types have the same average treatment effect. And in that case, you can go back to selection on observables, which is the stuff that we discussed at the very beginning, right? There's no heterogeneity coming from unobservables. But the minute that this function is not flat, okay, then you're going to have heterogeneity in the way. And so how do you now identify this object over here, right? Because I wrote it as a function of this, but this is unobserved. So yeah, it's conceptually maybe an interesting parameter, but it's unclear how we can identify it. Well, what is shown in this paper is that the marginal treatment effect is point identified, okay, for all values of the propensity score or P in the interior of the support of this propensity score, and as follows: the derivative of respect to P of the expected value of the observed Y at the propensity score equal to whatever number you are choosing. It gives you the MTE at that number. So suppose that I put a propensity score of 0.3. I need 0.3 to be part of the support of the propensity score, right? And then I said, like, okay, the marginal treatment effect at 0.3 can be identified as the derivative with respect to P of the expected value of Y conditional on the propensity score being equal to 0.3. And this is called a local IB estimand, okay? As opposed to late, and this is going to be the first difference that we're going to find. This is thought from the get-go as a situation where you need the instrument to be continuously distributed. Because otherwise, you'll be taking derivatives and everywhere here, and everything is going to be a function of the propensity score. Everything is going to depend on moving the propensity score. So you're going to see very quickly that the marginal treatment effect approach requires a lot more from the instrument than the late. But as we're going to see later as well, it gives you a lot more as a result. Okay, so it's not that you're assuming more and you're getting the same, because that shouldn't happen. The late gave us this treatment effect for the compliers. Done. Here with the marginal treatment effect, we can obtain a lot more treatment effects of interest that later on we're going to call the policy relevant treatment effects. So we're going to have a variety of effects. And actually, what we're going to see in a minute is that we can write most parameters that we typically care about, including the late, as a function of the marginal treatment effect. So the treatment effect gives you, in a way, you can say everything. But to get a nice identification of the marginal treatment effect, you need a really nice instrument. Okay? Nice in the sense that Z needs to be continuously distributed, and it needs to move the propensity score a lot, because Z could be continuously distributed, but the propensity score could be between 0.4 and 0.6, and then you won't be able to say anything about the marginal treatment effect outside that. All right, let's see this argument, because I think you may like it. Let me write this: expected value of Y given that the propensity score is equal to little p, The law of iterated expectations, we can write it as expected value of y1 conditional on the propensity score being equal to little p and d equal to 1 times p plus expected value of y0 conditional on the propensity score being equal to little p equal to 0, 1 minus p, where we used that probability that d equals 1 conditional on what was I going to say, for p, again, use law of iterated expectations again. Probability that d equals 1 conditional on the propensity score being equal to p. And then here we have then the inside probability here is just the probability that d equals 1 conditional on z. And that this over here, of course, is just the propensity score. And the expected value of the propensity score conditional on the propensity score being equal to p is p. So this is what we use over here and there. Next, note that the event propensity score being equal to p, d equal to 1, using our model is, again, propensity score being equal to p, u less than or equal than the propensity score. Remember that b was equal to the propensity score in this notation. And so this is u less than or equal to p. And so putting everything together, we have that the expected value of y conditional on the propensity score being equal to p equal to the expected value of y1 conditional on u less than or equal to p times p plus expected value of y0 conditional on u greater than p times 1 minus p. Okay? We're good? All right. So now that's the starting point. This is the equation at the top. We have exactly what I wrote in the last line of the previous slide. So now let's write this as an integral. Okay, we have the expected value of y given the propensity score being equal to little p. It's just the integral from 0 to p of the expected value of y1 conditional on u being equal to little u, okay, times p times the distribution of this u conditional on u less than or equal to p du. Need to fit all this here. Let's see if it works. P to 1 now. Expected value of y0 u equals to little u 1 minus p times this density of u conditional on u being greater than p u. Yeah, fits. Okay. So now remember, U is uniform. Okay. So this density here of a uniformly distributed random variable in 0, 1, condition on U being less than or equal to P is just very easy. It's just 1 over P times the U. And this density over here of the uniformly distributed random variable for U greater than P is also very easy. It's 1 over 1 minus P du. And then guess what? This P and this 1 minus P, this 1 minus P and 1 minus P cancel out. So is this beautiful? So what we have is the integral from 0 to P of the expected value of y1 u equal to little u du plus the integral from P to 1, the expected value of y0 u conditional little u du. Now we're almost there. Almost home. Derivative of this with respect to P. Well, P only shows up in two places. Here and here. So applying the formula of the derivative is just the function you're integrating at that point. In this case, P is at the bottom, so it's minus the function you're integrating at that point. Well, that's exactly expected value of y1 minus y0 which is the MTE at P. Done. So as you can see, there's nothing really sophisticated, just, careful arguments and thinking about how to manipulate the objects, the places that they use somewhere. But that's the argument that shows you that the marginal treatment effect is identified by this derivative over here. Later on, we're going to see in the application how we actually implement practice. Okay. So, any questions about this derivation before I move forward? Utility of the marginal treatment effect. So, U here provides a single dimension in which we can organize heterogeneity. This is exactly what we're discussing a second ago in response to your question, right? So it's like you can have more unobservables, but there's an index here, U, that groups how we model heterogeneity in this case. And it turns out that this gives us the benefit that many quantities that we care about can be written as a function of the marginal treatment effect. And in particular, as I wrote here, it can be written as a weighted average of marginal treatment effects. So theta, which in a minute is going to be a parameter we may care about, generically, can be written as, an integral from A to B of the marginal treatment effect, where you weight people of different levels of heterogeneity according to some weight function. Okay. Of course, this is not that applies for any parameter, but what we're going to see is that a lot of parameters that we typically use can be written this way. So if you write something like this, and then you say, okay, the parameter you care about just can be described in this way. The parameter is going to be identified then if we identify the marginal treatment effect function, and assuming that the weights are either known or can be identified. Okay. So point identification follows from this local IB approach that we just described and proved. Okay. If we have support at non-zero weights, okay, whenever this guy is put in non-zero weights, we need to be able to identify the marginal treatment effect. Okay. The advantage of this is not only now that we can go back to things that we know, late or average treatment effect, and say, oh, look, you can write those parameters as using this representation, is that this tool will allow us to discuss new quantities that we were not discussing before. Okay. These are going to be what I'm going to call in a minute policy relevant treatment effects. It also clarifies one thing, which has to do with like interpolation and extrapolation. And the MTE gives us something that we can restrict or parameterize, which is actually, this function. This function is non-parametric, but in principle, we can model it. We can make assumptions. We can, suppose that we assume that it is linear in U, just to make a simple thing. Well, even if the support identifies MTU from 0.3 to 0.7, if we assume that it's linear, we can extrapolate now. Because the model gives us a structure that we can say something about areas that are not identified. Of course, under assumptions, but I'm saying it gives us that rule. Whereas in other settings that are more general, it's really hard to think about extrapolation. So, in a way, and this is going to be essentially the content of the next lecture, okay, not today, this framework is going to allow us to extrapolate. It's going to allow us to make statements about the areas that we cannot identify. So, AT, average treatment effect. Well, the average treatment effect is an unweighted average of marginal treatment effects. Is this integral from 0 to 1 of the marginal treatment effect times 1, so the weights are 1, and the U, uniform. And that gives us the average treatment effect. So the average treatment effect is point identified if 0 and 1 belong to the support of the propensity score. This should be obvious because if we just look at the formulas we derived, the expected value of y conditional on the propensity score being equal to 1, well, that is the expected value of y1 conditional on u less than or equal to 1, okay? And this is exactly the expected value of y1. So imagine that you had this condition, right? That 0 and 1 are in the support of the propensity score. Well, condition on everybody with propensity score equal to 1, those are individuals that always choose D1. Well, that will give you expected value of y1. Then condition on everybody that has P0, that will give you everybody that has P0. And then you can take the difference of those two and then you're done, okay? In a way. So that's the idea, okay? The problem is that this requirement is what is called a large support condition, and often requires this instrument to be able to move the propensity score all the way from 0 to 1, which tend to be a strong requirement. And as I wrote here, it essentially means that there exist values of the instrument Z1 and Z2 here, such that every agent with Z0 will never take the treatment. Okay, so propensity score is 0, whereas every agent with Z1 will always take the treatment. Okay, so the propensity score Z1 is 1. Okay, and essentially means that you have random assignment because you're just choosing. You just set 1 equal to Z0, you get D0. You set Z equal to Z1, you get D1, right? And so you can assign people to treatment and control. This is a severe demand that you place on the data. So what do I mean by all this? This representation is true, okay? That doesn't mean that we're going to identify the average treatment effect because you're saying, like, oh, great, so now I can talk about the average treatment effect. Well, most often you will not be able to because you will not have this condition, okay? And that's something, again, that we're going to discuss next class. That's why the representation works, is elegant, and it's intuitive. That doesn't mean that you can take it to the data easily. Okay? All right. Average treatment on the treated and average treatment on the untreated. Again, there are weighted averages of the marginal treatment effects. The ATT can be written, it says C problem set, is not in this problem set. Okay? But it was at some point in the problem set. Can be written as this: the integral from 0 to 1 of the marginal treatment effect times this ratio. This is the weight of the ATT. Okay, is the probability that the propensity score is greater than or equal than U divided by the probability that D equals 1. Unconditional probability, integral du. So here, it means that, I wrote here, low values of U are more highly weighted. Okay, and why is that? Well, because remember, people with low values of U are those that choose D1 more frequently, and those are the treated, right? So it makes sense that when you just look at marginal treatment effect, you put a higher weight, okay, on those that have small values of U because you're looking for the average treatment on the treated, okay, on those that have D equal to 1. And so, again, if you just look at this, this is something that you can get from the denominator here, something you can get from the data, and the numerator, as well, if we can have some way to know or estimate the propensity score. So that's why I wrote here the weights are known or identifiable, and they integrate to 1. Okay, so here you see that it looks exactly as the formula we derived before: A to B, MTE, and some weights. And so for every parameter you care about, the goal would be to just find what these weights are. You don't have to do it because there are papers that have done it already. And actually, the one that we're going to discuss next Tuesday have like big tables that we're going to see where you see all these functions. Okay, we may see one today. I don't know. So the analogous argument holds for the average treated and the untreated. Okay, so ATU here it's just the same, except that now this is reversed, and then high values of U get higher weight because people with high values of U choose 0 more often, and so that makes sense. Okay, and so here you have another example where if you find the right weights, then you weight the MTEs this way, and you get the parameter. Next, late. You write late, the weighted average of MTEs. Yes. Suppose that P of Z is greater than P of Z prime. Two values, Z prime and Z. Okay, so the late from Z prime to Z, okay, you can write as an integral from 0 to 1 of the marginal treatment effect, weighted by omega late du, where omega late is this stuff over here. Okay. And this actually makes sense if you just think about it this way. Let me just do a line here. This is Q. Let me put here, which one is it? P Z prime. P Z. So think about it this way. If you just draw this line, you can see people with U's over here. Okay, these are always takers. Again, here think about the value of the instruments only taking these two values, Z and Z prime, as in late, right? Well, the model, remember, D is indicator, U is less than or equal than the propensity score, right? Well, if you're below here, you always have 1 because U is below this. For this value of the instrument, you're below this, so just 1. For this value of the instrument, of course, you're also below. Okay, so then you choose 1. Similarly, if you're on this side, you choose 0 for both. Never taker. Your U is so high, it doesn't matter what is the value of the instrument. You're just going to never take the treatment. And then you have people over here. These are the compliers. These are people that choose 1 if the value of the instrument is Z, okay, but choose 0 if the value of the instrument is Z prime. And so now look at the weights that you get for late. Well, you're just putting uniform weight on compliers. And no weight on anybody else. And that's exactly what the late is. Right? Okay. So late as a weighted MTE. Something interesting is the limiting case. Here we have this thing. What happens? I'm moving my fingers and you don't see my fingers. But what happens if this area where I wrote compliers, like you shrink it, right? And then if you get these two guys close to each other, and then imagine a situation where PZ prime is here or PZ prime is here. So PZ prime gets closer and closer and closer to PZ. And so you just have a smaller set of compliers. Well, you can model that by taking a limit. Okay. And then you work it out. And what do you get? You get the marginal treatment effect. So the marginal treatment effect is a limiting marginal version of the late. Okay, whereas the late gives you a discrete change between 2 points. The marginal treatment effect, as we show, gives you a derivative. It's just a marginal change. Okay. And then formally you can see it here. So it's a marginal version of late if you want. Now, finally, what about the IV estimand? Okay. Remember, the IV estimand is something that we said is always well defined, right? You just do IB. What are you identifying? Well, under the late assumptions, we know that if you just have two these binary and these binary and whatever, we saw that the IB estimand is essentially late. Now, what if more general in the case where Z is continuous? Or suppose here that J of Z is just a function of the instrument, which is the instrument that you're using. Okay. And then you do IB, and then let's call this IB estimand beta IB comma J because you're using that function of the instrument as an instrument. Well, then this is the covariance of JZY, covariance of JZD, and then you can show that this can be written this way, where the weights for the IB are this function over here that is kind of involves expected value of the instrument conditional on the propensity score being greater than or equal to U minus the unconditional expected value of this instrument times the probability that the propensity score is greater than or equal to U divided by this covariance. Okay? The weights, are 0 for U's that are outside the support of P, and they integrate to 1. Okay? But this weight here will have the feature that if you look at this quantity over here, there will be both be positive and negative. Okay. And so what this is saying is again, this is an unpleasant feature of having weights that are positive and negative because you can have situations like the one we described in late without the monotonicity assumption, or in general when we talk about IB in the heterogeneous case, that you can have a situation where people react in different ways to the treatment, but everybody reacts in a positive way. But then when you compute your, say, IB estimate here, you find something 0 or negative. You don't even identify the sign just because you're multiplying things with negative weights. And so it might lead to misleading interpretation, okay, of what's going on. So at least you want weights of these expressions to be always non-negative, because that way, if you're in a situation where like everybody responds in the same way with the same sign, you certainly are going to find that with your estimate. That's not the case here, except if your instrument is the propensity score or a monotone transformation, but let's say the propensity. If you use as an instrument the propensity score, you can show that these guys are going to be monotonic. Okay. So, and this, as I wrote here, is consistent with the results in Emmons and Angris, because in that paper they sorted the instrument by by the propensity score. So, it's a monotone transformation of the propensity score, and that works out, and that's why you get the result that you get. But in general, whenever the instrument is continuous, it makes sense to think about IB using the propensity score as the instrument. And you can work out this expression over here. Questions? Good. So let's talk now about policy relevant treatment effects. So what is a policy relevant parameter? Let me go over some stuff that I wrote here. The MTE framework partitions all agents in a clear way, by levels of this unobservable U. And I wrote here provides a foundation for thinking about quote unquote ideal treatment effects. And by ideal, I mean that you sort of like want to think in the opposite way as what I described before as, reverse engineering. You can just want to think about what's the policy that you care about, and then you think about how you identify that parameter. The average treatment effect is one that receives the most attention in the literature, right? So like we just go, people talk about average treatment effect, average treatment effect, average treatment effect. But, if you just talk to somebody who does apply work and then cares really about policy and so on, very rarely they will tell you the policy average treatment effect is a parameter that is policy relevant, right? Because, in that parameter, like think about D is I don't know, going to college and it returns to education, then the average treatment effect tells you what would be the effect of sending everybody to college versus not sending anybody to college. And then, most often people will say, well, I'm sorry, but that's not a policy that is relevant. Okay. Because, we don't really care about what would happen if everybody goes to college or nobody goes to college. And, um, then in that setting, the average treatment of the treated has a more clear interpretation or relevance, perhaps, because it's the loss in benefit to the treated group from discontinuing D1. So again, you talk to college now is with the fact that how much you will lose from not allowing people to keep going to college out of those that are already going. Okay. Anyway, depending on the application, depending on the setting, okay, you will see that some parameters will make more sense than other, but they definitely should be application specific. So what I wrote here is that if we think about D being a choice, right? And agents choose D. And so now as a policymaker, you may not be able to enforce D. I may not be able to enforce that people just have a particular D so then you want to create, say, incentives. You want to evaluate policies that change the agent's choice set. Okay. So that make people choose in different ways. And so I wrote here, for example, suppose that D is attending college. Okay. The ATE here, as I said, is the average effect of forcing college versus no college for everybody. Okay. And perhaps the effect of college goers and shutting down college is also not very interesting. But for example, you can think about what if some people are not attending college because of cost, and then you can subsidize that with some subsidy C, right? So now what you're doing is providing incentives, changing the choice set of individuals. You still let them choose, and then some people will decide to go to college with an tuition adjustment, and some others will not. But then you can start thinking about exactly what is the type of policy that you want to evaluate. Okay. And then if again, when you start thinking about the policy first, most often these policies, rarely take the form of average treatment effect, average treatment of the treated, even though these are the parameters that we typically use. So what is a policy relevant treatment effect? Well, HECKMAN and VYTLACIL formalize this idea. They call it PRTE, right? Policy relevant treatment effect. And and the idea is to aggregate the effect on Y, again, it's going to be an average, some expectation of a change in the propensity score / instrument. So the change is some change that corresponds to a policy that affects the treatment choice, the things that we were describing before. How you model that? Let P star of Z star and C star be the propensity score instrument under the new policy. Okay. So suppose that Z was a subsidy that people receive to go to college, okay? But now you want to evaluate the possibility of a different subsidy, okay? It's a different instrument, a different measure that you want to change. And then you also allow for the possibility that the propensity score under the new law is different, okay? That the probability that you take out, changes is a different functional form relative to what you have with the original policy. I'm going to let D star, okay, we have the P star, Z star, the C star, and D star, which is just the one that you obtained from the selection model, except that, notice, the U here is the same. And then we define Y star as D star, Y1 times D star, Y minus D star, Y0. So again, notice Y1, Y0 are the same. And I wrote here at the bottom, an implicit assumption of this approach is that the policy does not affect the potential outcomes and the heterogeneity that you have in your problem. Okay, so people don't change, potential outcomes don't change. What you're changing is the policy. And so HECKMAN and VYTLACIL define the policy relevant treatment effect as follows: beta PRTE is the expected value of Y star, okay, minus expected value of Y, expected value of the outcome under the new policy, minus the expected value of the outcome under the old policy, divided by the expected value of the treatment under the new policy, minus the expected value of the treatment under the old policy. Okay? the mean effect net per person of the policy change. And that's a policy relevant treatment effect. Let's see a bit more. Turns out you can show that the policy relevant treatment effect can be written as a weighted average of a marginal treatment effect. Again, okay? And I said before, the marginal treatment effects will allow us to evaluate parameters that were harder to think or conceptualize before. All right, so you can show that this policy relevant treatment effect can be written this way, where the weights are given by this function over here. The function involves a ratio of statements that includes both the propensity score that you have under the old policy and the propensity score that you will have under the new policy. Okay, so here FP and FP star are the distributions of the propensity score, the old one and the new one. And, what's important here is that the support of the new propensity score must be contained in that of the old propensity score. So that gives you the extent of the policies that you can evaluate. Okay, you might say like, well, the one that I wanted to evaluate had a propensity score was outside this. Well, you won't be able to do that unless you make some extrapolation assumptions, because all that you can identify, remember, is the marginal treatment effect for values that are in the support of P. So suppose that again you have a propensity score that takes value from 0.2 to 0.8 and it's just linear. You can evaluate policies that have a different shape that are linear in the other way or flatter or whatever, but always between 0.2 and 0.8. And you won't be able to say much about 0.8 to 1, and unless you use some extrapolation that we can see later. So what I wrote here, the reason for this is that we can only identify the MTE on the support of P. So this requirement, of course, makes sense. And restricts to interpolating policies versus extrapolating policies, which is what I said before. We still need a continuous instrument, okay, because that's what we need to estimate all this. But you can see that then this representation that we've been discussing before allow us to, characterize this type of parameters that before were harder to conceptualize. So consider as an example to conclude this thing of the policy relevant treatment effects. Suppose that you want to evaluate two policies that are not the current ones. Okay, so it's like, what if we increase tuition by we decrease tuition by 20%, or what if we decrease tuition by 40%? Okay, well then you will have two situations: DA indicator U minus this, okay, YA, the same thing for the DA, and you have the same thing for policy B. The policy relevant treatment effect is just gonna be this, okay? And then you're just gonna write the weights. If you identify the marginal treatment effect function, you can find this type of objects, okay? And then in the example that I said, suppose that you decrease the tuition by 20%, whatever, you can do it sometimes by assuming that PA is equal to PB, right? So you don't have to change everything in any analysis that you want. It could be that CA is just 0.8 of the old Z, and that CB is like 0.7 of the old Z, and it just changed the instrument but did not change the propensity score. So if you understood that, then you can see that here at the bottom, I wrote that the late is a policy relevant treatment effect. Okay. Policy A, every agent receives Z prime. So the propensity score is not changed. The instrument is set to Z prime. Policy B, every agent gets Z. Okay. And then you have that the propensity score doesn't change. Z is CB. You write it down and you'll see immediately that the policy relevant treatment effect for these two policies is exactly the late. Okay. So again, late in some cases may be a parameter that you really care about. So you can criticize late as a generic parameter of interest. That doesn't mean the late will not be interesting in some settings. In some settings, in particular, as I wrote here, if Z is something that you can actually move, then it may be a policy that you care about. But these are the two policies that you are able to identify with late. It's just these two. Everybody receives that, or everybody receives the other one. Right? That's the effect that you find. With the policy relevant treatment effect, which requires you to identify the marginal treatment effect, which is, as you can see, it requires stronger assumptions. You can evaluate all sort of policies. As I said, you can keep the propensity score the same. You can change it. You can consider different z's that are like fractions of other ones that you had before. You you can increase jumps on propensity score. You can, if you have policy A, could be that some fraction or scaled up for alpha greater than 1 of the old propensity score. So you just bump everybody up. You introduce something that is going to increase take up. Okay, you can model any of this. And we're going to discuss some of this, I think, next class. Questions? All right, so then let's now move to this empirical application by Canay, HECKMAN, and VYTLACIL. And this is going to take us to the last part of today's class. So what's the application? The application is the usual returns to schooling, okay? They have a sample of white males. They're like about 1,800. Y is roughly here log average hourly wages. D is attending college or not. X contains a lot of things, and I want to show you in the next slide, but I wrote here the usual suspects. And Z are taken from a variety of other papers. These are like different instruments. And, for example, you can talk about distance, the presence of four-year college in the county of residence at age 14, local wages in the county residence at age 17, local unemployment at age 17, average tuition of public four-year colleges in the county of residence. These are instruments that have been used in a variety of other papers. They list them all in a table we're going to discuss. But we're going to use these instruments. So the analysis so far has been conditioned on X. I said that as we were talking. This clearly will not work in practice when you see the list of X's that we have. Non-parametric conditioning leads to the usual curse of dimensionality, implementation issues, all sort of issues, including also this requirement that we have in the support of the propensity score, that even if we just get rid of the curse of dimensionality, we'll have issues that we'll have to deal with in a second. So this is something to think about. This is one of those issues that when, you write the theory, you say, I don't want to cover this because it could be messy, it could be application specific and so on. But when you go to the actual application, you have to seriously think about how you're going to accommodate these things to your setting. So what they're going to do here in this paper is they're going to impose some semi-parametric structure. Right? So the model is not going to be fully non-parametric. It's going to be semi-parametric. There are going to be some parts that we're going to have to model. And then we're going to be adding layers in particular because, we'll have to deal with this limited instrument support that we discussed before. All right. So here you have a table. This is a table of translation, right? Y is our Y. S in this paper is our D. X here in this paper is the covariates, the X that I'm using, okay? And Z in this paper is sort of like everything, the covariates and the instruments, okay? So Z minus X are what I call Z, which is you can see over here, Z minus X. The X's, you see here how many variables. AFQT, mother's education, number of siblings, average logs earnings in the county of residence, average unemployment rate in the county of residence, urban residence at 14, cohort dummies, years of experience, average local log earnings in 91, local unemployment in 91. I have all these things, right? And then the instruments that I said before. And then we want to use with also the papers that have used that instrument in the past. Okay, this is a translation so that you know what they're talking about when you look at the paper and when we go over the tables as we move on. So what's going to be the semi-parametric MTE? Well, we're going to first model the potential outcomes. Okay, potential outcomes, we're going to make them linear in covariates. This is the part that we're being semi-parametric. Okay, The potential outcomes are gonna be a linear function of the x's plus some error term that we assume has 0 conditional mean. Okay, and then of course, the observed y is always going to be d times y1 plus y minus d times y0, right? And so when you take the expected value of the observed y, condition on x, condition on the propensity score, you work it out using this expression over here, and you get this. You get that it is x delta 0 plus px delta 1 minus zeta 0 plus this function kappa of p and x, where, well, it's not kappa, it's k. K of p and x, where k is just the integral from 0 to p of the expected value of b1 minus b0. These are the b's over here. Condition on x equal to little x and u equal to little u, which comes from this condition du. So that now, if you take the derivative, remember, the marginal treatment effect is the derivative of this expression with respect to p. You have the marginal treatment effect of p for each x is now this function over here is x times delta 1 minus delta 0 plus the derivative of this function k here with respect to p. As I wrote here, this is almost a partial linear model. Okay, a partial linear model introduced by Robinson in 98. You can see here, if you just look at the top, that x and px enter linearly. This is exactly this part over here. And they also entered this through the unknown function here, k. And this is a problem because k, p, x depends on x. And again, we see that x has a lot of components. So now we have this like non-parametric function here that depends on all the x's, okay? And so now we have x and px here, and then we have x and px here, which also introduce identification issues, right? So you would imagine that in general, you won't be able to identify these components, the linear components, from the nonlinear components separately. So what do we do? What Canay, HECKMAN, and VYTLACIL do is to introduce an assumption. This is a very strong assumption. We're going to discuss it and actually relax it later. It says that x and z are independent of b's and u's. Okay, so essentially, it's saying that the x's over here are exogenous. Okay, so under this restriction, when you just look at this function k, which is this, well, here we're saying conditional. These guys are independent of this, so this expectation here is such that you can get rid of this x. And now it's nice because this function only depends on p. And so now the non-parametric component is a function of a scalar random variable, which is p. And then you go and rewrite the model, and it looks like this. So now we can do a partial linear approach. So how does that work? I don't remember if we did it last year in 480, but sometimes they're in all exams. You just take this, you take conditional expectation with respect to p. So you have the first term, conditional expectation with respect to p. Second term, conditional expectation with respect to p. So the p pops outside. And then last term is just kp because you're taking conditional expectation with respect to p. The other one disappears. And then when you subtract, do this minus this, you have this expression over here with all the tilde variables. Well, the tilde versions are just the original variable minus the conditional expectation with respect to p. You do that for the y's and for each of the x's. And this is the model that you have, which is linear and x and p, or x tilde and p. Okay? So that's how this works. You first estimate these conditional expectations non-parametrically, okay? But that is not a problem right now because p is a scalar. And so it's just a non-parametric estimation of, think about whatever, not a Watson or anything else, okay? But it's a simple problem. And once you have those conditional expectation estimated, then you can recenter and then run the linear regression later on. That's the partial linear model. going back to Amilcar questions at some point. Here you see here how estimation is popping out, and then you tell me like, oh, I want to estimate the propensity score using some fancy thing. Sure. I want to estimate this condition expectation using some fancy thing. Sure. Then you will have to work out the properties of the semi-parametric estimator. But that's it. Okay. So to recap, we're going to estimate P of X, the propensity score, using a logit or probit in this case. But you could do something else. In the paper, they use a logit, I believe. Okay. Once you have that, you're going to construct the tilde versions of the random variables, which requires that you estimate, expected value of whatever conditional on your P hat. Okay. This is scalar, so this is easy to do. You know that. Then, once we have the tilde versions, we're going to do linear regression of y on x, then the interaction of p times x. And that was going to give us the estimators of the delta hats and so on. And then finally, we're non-parametrically going to regress y minus this minus that on p hat to get an estimator of the function k. What we want is the derivatives of k. So typically, you can do this in one step. What procedure will give you the function and the derivative in one step? But one thing you can do is local linear estimation, right? A local linear regression, local quadratic, and then you do that, and you get the function and the derivative. Remember, all in one step. So if you just need the derivative because the marginal treatment effect is just going to be this, then you can just do local linear estimation and you get both the derivative and the function at a point. And that's how we do it. And we have the marginal treatment effect for each value of x and p. Okay. So comments. This k can only possibly point identify for p comma x in the support of px. Okay. So again, think about the general version of k, not this one. Okay, the one that depends on both. For a fixed x, you need p to belong to the support of the propensity score condition on x. This is something that Raul mentioned at some point earlier. Okay. However, instead of using k of px, just using k of p, given the restriction that we introduced, then all we need is p in the support of the propensity score, which is of course larger than the conditional support. Okay. Now, so that means that this assumption that we impose address the support issues. Okay. But this is a big assumption that we're going to discuss. But these are important issues that appear all the time. Okay. So you need to do something about it. So look at this picture. So here is the joint support of P and X, right? So if we I'm going to screw this up, but just do slices like this, right? So you can see that you have something like this, have something like this, this. Do you see how conditional on X, right? The support of the propensity score is quite restricted. For example, condition on these really small values of X, look, the support is between here and here, and you have nothing over here, right? And then if you keep slicing for any other values of S, you can just look at this picture and realize, for example, for a large value of X, you have support here and here, and then you have nothing for low values of the propensity score. So this is for an index of the x's. That's why we can just plot it, okay? And all this is explained in this part of the table. But a row here is striking how small the support of P is for each value of the index x, okay? And then that tells you that even if, forget about the problem with estimation now, like you manage to just go for this function kpx, well, that would still be problematic moving forward because, again, for each x, you will need variation of P, and this will tell you that, for example, a K with low P and high X will not be identified, which is something that would fall over here, right? High X, low P, there's nothing. Okay? However, when you look at the unconditional propensity score for high school, and college students, well, you have here the black bars and the white bars. And, it's true that, have areas with low probabilities, but still pretty much everywhere. Right? There's a lot better. So the support of the estimated propensity score is almost full for both D0 and D1. Okay? Now, I wrote here a better way to separability. Okay, the assumption used in Canay, HECKMAN, and VYTLACIL is this one over here. So X independent of U is an attractive, okay, given the variables that we typically include in X's that we discuss, okay. X is still allowed to have a direct effect on the potential outcomes via the linear index, okay, but you're essentially assuming that X is completely exogenous. And that's sort of like unpleasant. So instead, one thing you can do is to use this assumption, right? This was later done in a different paper, not discussing now, but compare this with this. All you need is that condition on U, X is independent of B1 and B0. But, the heterogeneity of the individuals are still allowed to be dependent on all these characteristics that we observe. And so why is that? Because remember that this is the conditional expectation that we had. And then if condition on U, X is independent of this, then you can go and take this step, which is exactly the step that you need in the paper. Okay. This is certainly, with this, I don't want to criticize the paper by Canay, HECKMAN, and VYTLACIL at all, but it's a reminder to you who sometimes will write more structural papers, or those of you that are doing theory papers. But sometimes, one is carried away by imposing an assumption that, gives you to where you want, and you never take a step back and saying, like, can I, where did I use this assumption exactly? Okay. And what was the role of this assumption? And, can I get away with something milder than this? Okay. Because this, as you can imagine, you look at this expression and it's obvious that this is sufficient and that this is much weaker than this. Okay. So what tells you is that, sometimes you work, these are large projects, you have a lot of layers, and then you just solve one layer and move to the next one. Okay. And you keep going. And then sometimes you don't look back. It's a good practice to always get used to this thing where, like, once you impose an assumption and you get a result, just look at the result again. And then you ask yourself, where did I use this assumption? Can I get away with something milder? Yes, no, and so on. All right. So again, one benefit that I didn't discuss before of this assumption that the K function doesn't depend on X is that if you take the derivative of the marginal treatment effect with respect to P now, okay, the slope of the marginal treatment effect doesn't depend on X. And that's great because you have separability. You have something that depends on X, something that doesn't depend on X. And I take a derivative, boom, gone. So the slope of the marginal treatment effect does not depend on X in this model, which is something you could test. I think they do it, but you could do it. Okay. This plots over here the marginal treatment effect with confidence bands. Okay. And what you see, okay, is that this is a semi-parametric estimation. One thing I want to tell you is remember that in a model where there's no unobserved heterogeneity, the marginal treatment effect would be flat. Okay. Here you see that the marginal treatment effect is not flat, which is giving you the, the obvious indication that in this context, selection of non-observables is an issue. Right? there's evidence of that by just looking at the slope of the marginal treatment effect. So they did in the paper using the semi-parametric case. They usually did a normal model, okay, where you just put some structure. And then you see how sometimes, the parametric structure imposes monotonicity by itself, right? Which is not imposed here, although it definitely looks monotone. But also may introduce sometimes funny behaviors at the tails where you don't have a lot of data, right? Remember, that's where things starts being fishy. As I wrote here, the unconditional support of the propensity score in this application is here. It's between 0.3% to 97.8. So it varies a lot, but still you can't get to 1 or 0, right? And then, everything that is going on at the tails here is just driven by the parametric assumption. All right, we're getting to close to the end. Last part is that we can test the null of no unobserved heterogeneity, right? Which is again related to this flatness that I said over here. How can you test that? They here provide 2 tests for this null hypothesis of no unobserved heterogeneity. Okay. And the idea is the following. Recall that this is what we have in the model. No unobserved heterogeneity in the treatment response would be if and only if this expectation over here is equal to a constant. It's just constant. And so that simplifies a lot of things, because that means then that this function k of p is just p of z. In other words, what we're saying is that this is linear in p for each x. So that's an immediate consequence of no unobserved heterogeneity. So one way that you can test this, okay, and this is what I said, when you can write the same thing in terms of the marginal treatment effects being flat. But one way you can do this is just define this kappa function here semi-parametrically, or as a polynomial of some degree, and then test the hypothesis that all the coefficients that are beyond the beta 1, okay, beyond the linear ones, are 0. And so if you just go now and look at the results, you see here you have polynomials, degree 2, 3, 4, 5, and then you have the p-value of the join, the null hypothesis that I said, and then, no unobserved heterogeneity is rejected here when the level of the polynomial is small. It's not rejected when the level is high. So in panel B, what they do is just test, chunk of these functions. Like if you want, and instead of the derivative, they just test for intervals, and they do that by using these lates, right? So what they do is, like, imagine you partition the support into intervals. These are the intervals over here: 0.0 to 0.4, 0.8 to 0.12, 16 to 20, and so on. Okay, and then you then test the hypothesis that the late from these 2 points to the next 2 points are exactly the same. Of course, you have a p-value for each of this, but then you're testing a lot of hypotheses here, so you have a multiple testing problem. So the joint p-value is about 0.5. So strictly speaking, at 5% you will not reject. At 10% you reject. There's clear enough evidence, I'll say, that there's unobserved heterogeneity. Right? But this, essentially panel A and panel B, shows 2 ways of asking the question of whether there is evidence of unobserved heterogeneity in this context. And that is all for today. So I'm going to answer questions now that you may have. And, the next class that we're going to have next week, it's going to be about extrapolation and trying to see how we can take all this MTE framework to partial identification setting. Okay, and that'll be all. So questions now.